Welcome! Let's take a look at linear programming in this video. When we program, we want to optimize. When we have a problem, we want a desired outcome, right? The solution. And to do this, we can utilize many methods, brute force or programming. I'll show you the difference between them and which one works in which scenario in this video. For now, let's look at an example. Miss Money opens a shop. At the opening ceremony, she wishes to give 6 prizes out. 2 choices work best, and so the prizes will be either a toaster or an air fryer. She sets out that there must be at least 2 of each of these prizes given out. How can she reduce the cost of the prizes in her pocket so that she can save some cash? So this requires optimization, and there's 2 of the aforementioned methods, brute forcing or programming. These use respectively tabulation or graphical method. We're going to use the tabulation method first. This method is advantageous when you have a small data set, but becomes tedious when you have a very large data set. We start by drawing the table. Let's recall the conditions that we set out. 6 prizes total, at least 2 each. Let's go ahead and write down the possible combinations. It's 2, 3, or 4, but conditions posit that we can't have 1 of each or more than 5 as it will exceed 6. I'm crossing out the combinations that can't exist, and that's because these will either not add up to 6 or exceed 6. So let's say toasters cost 20 and air fryers cost 30. We need to find which of these 3 possible combinations gives the lowest value. In the sample calculation, I'll be using 4 air fryers and 2 toasters, which add up to a total cost of about, no, that's mistaken. I put 40 instead of 30, sorry. To about 160. Here's the rest, and from this we can see that 4 toasters and 2 air fryers are the optimal combination. But let's take a moment to think about something. What if we had to give out 1,000 prizes and we had to give at least 237 of each? If you were to tabulate this, not only would it take the rest of eternity, but it would take about 500,000 calculations. Now, I don't know about you, but I didn't want to be doing 582,000 combinations. I have better things to do with my time, and that's where programming comes in. Programming does repetitive tasks for us. So let's look at this through the eyes of a programmer. We have 6 prizes, 2 each. First off, we're going to graph this. To draw our graph, we set the upper bound, which is 6, and we draw a line between them. Next, you add your limits. In this case, there must be at least 2. This orange area refers to the feasibility region, and that's where the possible combinations exist for this problem. When we see graph, we must think of equations, and hence, we derive an equation for the cost. The cost is the price times the amount, so 20 times toasters and 30 times air fryers. Here, we have to make a choice to set one of our variables, toasters or air fryers, as the x and y axes. This is important as we'll be deriving an equation where one variable, the y-axis, is related to the other variable, the x-axis. I arbitrarily chose t, but a would have worked as well. Through deriving, we find that t is equal to the cost over 20 minus 30 over 20a. Now wait a minute. That looks just like y is equal to mx plus c, the linear equation. Yes, we can say that y is equal to t, mx is equal to negative 30 over 20a, and c is equal to cost. So let's graph it. Such as the Swiss Army knife of maths, that by graphing the function, we will find the point of optimization. In this case, c is an unknown, but we don't actually need c. So to do this, we make c arbitrary. This means we take a line with the gradient, in this case negative 30 over 20, and give it the freedom to move up and down. We essentially slide it up and down until it has a point in which it contacts the region of feasibility. Now, this all sounds very complicated, but you'll see how simple it is. First off, let's look at the gradient. We're going to try and find a line that has a similar gradient to -30/20. We take that line and now we slide it ever so slightly over the graph. There we go. That's the point at which it first contacts the region of feasibility. This point, as it turns out, will be the local minimum of the function and lead to the optimization point because it will have the lowest cost. So let's work that out. The coordinate is 2, 4, and 2, 4 in our equation will determine the minimum cost. Recall x is a and y is t, sub that into the cost and we get 140, just like the tabulation method. You're a pro now, so let's go through a speed run. 1000 prizes, 237 minimum of cost a is equal to 37 and t is equal to 34. Plot the graph, plot your limits, get your feasibility, then work out your equation and derive it in terms of one variable. Work out the gradient and then slide it over the graph. Find the point of intersection and bam, you've got your coordinates, and with those coordinates you can work out your cost. And just as an example, I did the reverse of that, and you can see that by optimizing you will save over 4%.